Good evening, everyone. I'm Karthik Jadhav. So, welcome you all on today's problem solving session of week 5. Okay, so, let's begin today's session. I hope my screen are visible to you. Okay. Okay, so, let's begin today's session. Again, I welcome you all in today's problem solving session of Soil Science and Technology course. So, course is basically run by Professor Chakrabarti from IT Kharagpur. So I'm Karthik and Premier Fellow currently at IIT Roorkee. Yeah, so this is my contact information. So if you have any query related to this course content or if you have any doubt regarding previous problem solving sessions or any concepts, you can directly write in the given email ID or you can also chat during the live session. Also, I'm whatever I'm covering since last 4 week, I am uploading that also in this YouTube channel. So I request you to uh, go to through this link and watch that uploaded content. And also, I'm uploading lecture material in this Google Drive. I hope you are also receiving it through email by NPTEL team. And I'm I would like to request you to provide your valuable feedback regarding regarding any update you required or anything you want to tell me like where I can upgrade myself or where I can improve. You can write to this Google form, and that will be really helpful for me to develop more informative and knowledgeful content for upcoming weeks. Okay, so today's we are at week 5 and this week we have covered about silicate clays, basically silicate clays, its types, what are the sources of charges on soil colloids, then one important concepts called cation exchange capacity and sorption of pesticides in soil. Right, so before we begin, let me quickly recap what we have covered till now. Right, so till now we have overview about the soil, why it is important. Right, soil and water, as we know that in the face of climate change, ongoing anthropogenic activities, our natural resources are degrading nowadays. Right, and the per capita ability of these natural resources is declining exponentially, particularly for developing countries. Now, due to that, if do not have proper understanding of this natural system, then it will lead to the condition, a very bad condition, and that is directly related to our agriculture and our construction, whatever you say that is related to the soil. That's why it is very important to understand this. And then we have started about basics of soil, starting with its classification called soil taxonomy. Then we have uh, briefly covered in week 2 and week 3. That is, we have covered physical soil properties and how it is important in moving water from them. Then, since last week, we have covered about the flow of water into the liquid. So let's quickly recap that. So yeah, we in last week we basically defined that water movement within the soil is generally have of three types, that is saturated flow, unsaturated flow, and vapor movement, right? And the saturated flow, when all the soil pores are filled with water and whatever flow will occur of water, that is called saturated flow. And whenever larger pores in the soils are filled with air, right? So whenever after saturated flow, the water will drain by gravity and all these large pores will empty. After that, whatever flow will occur through the small pores It's called unsaturated flow, and vapor pressure difference develop vapor movement in the soil, that is called vapor movement in soil, right? Then we have covered important concept of different coefficient, right? Like what is saturated soil, field capacity, wilting coefficient, and hygroscopic coefficient. Then we have also covered about soil aeration and how what are the major factors that affect the soil aeration. And one of the important law related to the soil aeration that we have covered is a Fick's law, right? So it states that the how the concentration in the concentrated concentration gradient drives the uh, movement from one place to another place through Fick's law. Then we have also covered redox potential, right? So it is basically about oxygen, right? How oxygen is accepting, either it is a releasing, that define the redox potential. And then we have also briefly covered the soil temperature and why it is important for us, that also we have gone through. So before okay, so now let's move on to the week 5 summary of week 5 content. So in week 5 we have started with the lecture 21, and in that uh, we covered about the silicate clays. So what is silicate clays? So before we define silicate clays, let's understand the soil colloids. So soil colloids is a two-phase system where a finely divided phase is dispersed in another phase, right? And its example is solid in liquid like clay in water, and liquid in gas like clouds in atmosphere. Then soil particles, generally soil colloids, whenever soil particles having a size less than 2 micrometer, then it called soil colloid. And soil colloid includes a combined clay as well as humus fraction. And if we specifically talk about properties of soil colloids, so soil colloids are extremely small size. They have a very high specific surface area, have a charges, either it is a positive charge or negative charge, but predominantly it is a negative charge. That's why it's play a very important role in cation exchange capacity of particular soil. Then it's also affect adsorption of cation anions, and also it affects the adsorption of water on the soil surface. So soil colloids are extremely small, as we specified. It is less than its size is less than 0.0, uh, it's less than 2 micrometer, right? Or 0.0002 mm, right? And it is a chemically active particle in the soil that have a high surface area and responsible for soil ability to retain nutrients and water. Then we have defined soil colloids. Generally, we can define in 4 parts. So that either it is a crystalline silicate, non-crystalline silicate, iron and aluminum oxide silicates, and organic silicates or colloids, right? So these are the types of colloids. So colloids are generally of 4 types. So first is crystalline silicate. So crystalline silicate clays, major example of this type of colloids is kaolinite and smectite. And this is the most common type of clay minerals, and it have 2 to 4 sheet per layer, as we have shown the structure of this, right? It is like this, 2 to 4 sheet per layer, and have a layered structure, right, with a varying degree of swelling. And the most common example of this is kaolinite and smectite. While second one is a non-crystalline silicate clays, and it have a lack of defined and crystalline structure. It means it do not have a layered. it have a non-crystalline and non-uniform. It is the mixture type of silicate clays it contain, and it have a high capacity to absorb nutrients and water, right? And it found in volcanic gas, and general example of this kind of silicate clays allophane and immogalite, right? And third one is iron and aluminum oxides colloids. So it generally found in highly weathered soil like tropical area or tropical soil, and do not swell, and it have a low cation exchange capacity. As a result, it also have a low plasticity and stickiness. And also it influence the soil color. So this presence of iron and aluminum in soil that will resulted into the changes in the soil color. So either it is a reddish color or yellowish color whenever iron present in soil, if you observe, right? Then fourth one that is a very important, that is organic colloids. So humus, so this is the smallest among all the colloids, and generally it is a decomposed organic matter that retains nutrient and water. So the organic colloids have highest nutrient retention capacity, and net charge of this type of colloids is always negative. It also have a highest cation exchange capacity, right? Because it is the smallest, and it's also helps in improving the soil structure and water retention. Hi, so let's continue. Right. So in continue with this week 21 content, we have covered about the silicate clays classification based on the arrangement of silicon oxide tetrahedra, which form the different structures, namely nasosilicates, sorosilicates, inosilicates, cyclosilicates, phyllosilicates, right? And among all this, and how we are classifying this is based on the arrangement of silicon of SiO4 tetrahedra. Either it is separately attached, either it is formed in two or more SiO4, either it is a double chain, single chain, also it is a cyclic kind of structure. And among all these structures, the important one is phyllosilicates, as they are dominant in soil clays and influence the fertility, nutrient holding capacity, as well as shrinking and swelling behavior of the soil. Then we have covered about the basic structure of silicate clays, that we can classify it as a silica tetrahedron and tetrahedral sheet and alumina octahedral. So generally silica tetrahedron that coordinated with the, so silicon atom in the silicon tetrahedron is coordinated with the four oxygen atom around them, as you can see in this figure, and the angle between these two oxygen is 109 degree. While in case of aluminium or magnesium octahedra, it is coordinated with the 6 oxygen atom or hydroxyl group, as you can see in this from this figure. So this is the aluminium, or it is either magnesium. So it is coordinated with the surrounding 6 oxygen or hydroxyl groups. And then by understanding this, we have classified silicate clays arrangement, right? So that we can classify this as a two type, that is trioctahedral and dioctahedral. So what is a trioctahedral? Generally, in general, we can classify them as a one gem one clay, two gem one clay, right? Based on trioctahedral. Okay. So one gem, what is one gem? One clay type of silicate clays. So one gem, one type of clays are having one sheet of octahedral and one sheet of tetrahedral, right? Generally, one gem, one clays have a stable in nature and non-expanding, and is generally commonly found in a tropical soil, as we have covered this kaolinite, right? Generally, we found this type of structure very stable in a very stable condition. So it means it is not generally eroded, right? Then, if we talk about two gem one clay type of structure, so in that we have two tetrahedral sheet, and that two tetrahedrals in between two tetrahedral sheet we have a one octahedral sheet. So generally the example of this kind of silicate clay is pyrophyllite and talc. This kind of clays have a more reactive influence. It influences soil fertility, water retention, and cation action property. And if we talk about tetrahedral and dioctahedral clays, so generally it tri trioctahedral clays have magnesium rich and more flexible and generally found in basic soils, while dioctahedral have aluminum rich, that is more rigid and common acidic soil. After that, in next lecture, we have started about the sources of charge in the silicate clays. So generally, silicate clays we know that are dominant mineral constituents of soil colloids and primarily responsible for soil physical and chemical properties, right? Why? Because it influence water holding capacity, fertilizer retention capacity, and cation exchange capacity. Generally, silicate clays are composed of silicon, right? Oxygen, aluminum, magnesium, like structure, and it forming tetrahedral and octahedral sheets that stack to form various clay minerals. And we have we have shown that, right, based on number and combination of structural unit, we have classified we can classify silicate clays as a tetrahedral and octahedral sheet. Then generally two categories we can say it is one gem one clay, two gem one clay, or two gem one clay silicate, right? And so on. I'm not going on in this detail. Basically, what we need to understand from the silicate clays, or what we need to remember is the types of silicate clays. The arrangement of tetrahedral and octahedral sheet plays a major role, right? And generally, the most common group we can classify is one gem one, two gem one, and two gem one clays. So one gem one clay is most common example of it is kaolinite. So in that, as we know that one tetrahedral sheet and one octahedral sheet per unit, and it have a low shrink swell capacity and low cation exchange capacity, right? Because it is a stable soil and it have a limited surface reactivity, and it do not have more negative charge on its soil surface. Now, if we talk about two gem one clays, so it have a two tetrahedral sheet sandwiching one octahedral sheet. It have a higher surface area and greater expansion. It means it have a well shrink swell behavior. Its example is mactite, vermiculite, and illite. Lillite. Okay. Or smectite is also known as Montmorillonite. Okay. It also have a high shrink swell capacity as we have discussed, due to it have a high surface area. And the third one is 2 gem, 1 gem, 1 types of clay. And most common example of this type of clay is chloride. So it is similar to 2 gem, 1 clays, but it contains extra hydroxide layer in between. Okay. And due to that, it have a less ring swell capacity than smectite, or you can say 2 gem, 1 type of clay. Then generally, if we can talk about the sources of charges in silicate clays. So silicate clays acquire either it is either the negative or positive charge through different mechanism. And I'm not so let's briefly discuss what type of charges we have. So either it is a permanent charge or permanent charge. So what is permanent charge? So permanent charge is the amorphous substitution. It means it occurs during the clay mineral formation, and cations of a lower charge substitute higher charge cations in a crystal lattice. It creates a permanent negative charge. What does it mean? Whenever the whenever we have a silicon plus 4, okay, in our clay structure, if it is replaced by aluminium plus 3, so if you can see this charge plus 4 and plus 3, so whenever the cations of lower substitute the higher cationic charge crystal lattice in a tetrahedral sheet, that is known as amorphous substitution. An example is here. So it creates negative charge overall and attracts essential plant nutrients like calcium, magnesium, and potassium. While pH dependent charge, it means it is dependent on pH and it is not permanent, it is temporary. Right, I will cover this in next slides in detail. Then, as we have already talked about this in previous slide also, about common type of silicate clays, that is clay kaolinite, then smectite, then Mont Montmorillonite, right? So I'm not going this into in more detail here. And after that, as we have discussed about the this type of different type of silicate clays, why it is important for us to understand all this concept, right? So because all these properties will affect either it is a water movement, nutrient holding capacity, cation exchange capacity, soil erosion. Okay, so here we have defined about the silicate clays and how different silicate clays plays role in a weathering, or how what is the of role of silicate clay properties during weathering and clay formation. We know that weathering we have covered in our initial week content, that weathering is a process by which soil rock minerals break down into finer particles under influence of either physical force or chemical reactions. So due to that, we are generally classifying weathering as either it is a physical or chemical weathering. And if we talk about the stages of weathering and clay mineral formation, so we have covered during this uh, lecture 22 that whenever the soil is young and weakly weathered minerals, and we can say classified that young mineral as a primary minerals, and its example are light and chloride. So it characterizes form from alteration of mica and feldspar. They have a high nutrient content like calcium and magnesium. High nutrient content, here we are focusing on plant nutrient content. Okay. And this kind of soil, young soil, are loosely attached, and due to that, it have a low weathering resistance. And generally found in temperate regions with limited leaching. Then we have intermediate weathered clays, and its example is vermiculite and smectite. So it generally results from moderate weathering of mica and chloride. So smectite or Montmorillonite retains high water holding capacity, exhibits ring swell behavior. So it's example of intermediate weathered clays. And generally we have found this kind of soil in semi-arid to temperate environments. While third one is a strongly weathered clays, and its example is kaolinite, right? We know that kaolinite is very stable soil and it generally resists the soil weathering, and its characteristics is one gem one type of soil it have a one gem one type of clay silicates. So generally clay mineral formation is controlled by different kind of weathering intensity, and how weathering is generally affected by either physical force or chemical force. So physical force is like rainfall, wind, like that, right? And chemical is various chemical processes like dilution, hydrolysis. Then that we have covered during first week content, right? Hydrolysis, what is hydrolysis, what is dilution, what is chemical reaction that is governing the soil weathering, soil chemical weathering. Now, as we have discussed, there are various sources of charges on soil colloids. So, soil colloids, we know that is primarily composed of clay minerals, organic matter, and oxides, right? And generally, whatever charge that are present on this composition, either it is a clay minerals, organic matter, and oxides, that have two main types. So either it is a constant or permanent charge, and second one is variable and pH dependent charge. So constant and permanent charges are inherent to mineral structure, inherent. So it do not change with the time, and it is permanent, and it generally arises due to the amorphous substitution. And what is that? So during isomorphous substitution, where one ion in a mineral lattice is replaced by another of similar size, right? So size of this, if we talk about Si 4 plus and aluminium 3 plus, right? So size of this both ion is same. But what is difference? What is difference in this? The difference is charge. Here it is a 4 plus 4, and here it is 3 plus. So due to that, there is a ultimately creation of a negative charge, and this negative charge is a permanent. So in a clay minerals like Montmorillonite and vermiculite, substitute of silicon 4 plus by aluminium 3 plus in a tetrahedral sheet, or aluminium 3 plus by magnesium plus 2 in the octahedral sheet, generate net negative charge, and this charge is permanent and independent of any other soil properties, and it plays a very crucial role in cation exchange capacity, helping in retaining the plant plant available nutrients like potassium, calcium, and magnesium. While on the other hand, variable or pH dependent charges, so it generally depend on the pH of the soil solution, and are common in the soil components like organic matter, iron, aluminum oxide, and kaolinite. So they arise due to the protonation or deprotonation of hydroxyl and carboxyl groups. So hydroxyl is OH minus and carboxyl is COOH groups. So at generally at lower pH or acidic condition, more hydrogen plus ions are present, right? Leading to protonation, which results in a positive charge. While at a higher pH or alkaline condition, H plus ion dissociate from the surface functional group, leaving a negative charge. And is generally common in humus, iron and aluminum oxides, and kaolinite. So these are the importance of this sources of charges, right? Role in different type of soil clay silicates. I'm not going in detail, right? Or this is generally covered about the water holding capacity, availability of the plant available nutrients. Then in continue with the previous lecture, we have started about the cation exchange capacity of the soil, right? So whenever we are learning about silicates or silicate clays, the cation exchange capacity plays very important role, right? As we have discussed earlier also. So what is cation exchange capacity? So cation exchange capacity is a fundamental property of soil that defines its ability to retain and exchange positively charged ions. Basically, it is cations. So let me define here cations. Whenever the ions have a positive charge, that is known as the cations. So what is the cations? What are the type of cations? So, that is calcium, magnesium, potassium, ammonia, right? This is cation. Where what is anion? Anion is a ion having a negative charge like chlorine, bromine, iodine, then fluorine, then nitrate, all these are anions. And if we talk about the definition of cation exchange capacity, so we can define as the number of moles of positive charge that soil can absorb per unit mass. Okay, what is cation exchange capacity? Number of moles of positive charge that soil can absorb per unit mass, and it typically measured in centimoles of charge per kilogram of soil or milliequivalent per 100 grams of soil. So as if the higher cation exchange capacity of any soil, it means soil has a greater ability to hold and supply essential plant nutrients like calcium, magnesium, potassium, and ammonia. Generally, there are four factors that are affecting the cation exchange capacity. It is clay content, organic matter, soil pH, and soil texture. So clay content, if the clay content is higher, it means there are higher number of smaller particles. It means it have a higher specific surface area of that soil overall, and it carrying high negative charge. So which allow them to hold more cations, right? Generally, we have discussed this about clay, right? So among all the type of soil, clay have a higher specific surface area. Then organic matter. So again, organic matter is a decomposed organic matter or humus, has a very high cation exchange capacity, helping again for the nutrient retention and water holding. Then soil pH. So many colloids particles exhibit pH dependent charges, meaning their cation exchange capacity increases at higher pH levels. Right, as we have discussed in last slide. Then soil texture. So this again type of clays. If the clay content is higher, it means it have a higher specific surface area. Then we have also discussed about the methods of determining cation exchange capacity. So in that we have discussed about on soil to remove all the cations, we are putting the ammonium solution. Then the ammonium solution again replaced by the potassium solution, and then we are using this volume of ammonium solution at last for all the calculation. And if we talk about the cation exchange capacity in the different soil, so generally sandy soil have a very low cation exchange capacity because it have a higher surface, lower basic surface area, and generally it, its range is in between 1 to 5 centimole per kilogram. While for loam soil, it is in between 5 to 25 centimole per kilogram of soil. And as loam soil contains mix of clay and organic matter, while clay soil having the cation exchange capacity in between 25 to 100 centimole per kg in general, because clay soil have a higher smectite rich soil, right? So clay contain higher smectite rich soils. Then we know that a relationship between the pH and cation exchange capacity. So in highly weathered soils, cation exchange capacity is strongly pH dependent. At low pH, generally hydrogen ions occupies exchange sites, reducing the soil's ability to retain nutrients. While at high pH, more negatively charged sites become available and it increases the cation exchange capacity. Right? So generally, that's why we are saying that at lower pH, the transfer of leaching of nutrient is higher because it have a lower cation exchange capacity at lower pH. And how it is affecting? It will affect during leaching of various nutrients, heavy metal, emerging contaminants. Okay. And if we talk about influence of weathering on cation exchange capacity, so whenever soil is young, or young soil is also known as a weakly weathered soil. So it high in a primary minerals like feldspar and mica, and due to that it have a lower cation exchange capacity, right? So whenever this weathering of this feldspar and mica will happen from primary soils or primary minerals, it will form the moderately weathered soils, and it contains 2 Gem 1 types of clays like smectite and vermiculite with moderate to high cation exchange capacity, while highly weathered soils is dominated by iron and aluminium oxide with low cation exchange capacity, but low cation exchange capacity but higher anion exchange capacity, right? Then what is its practical influence importance, right? We know that it will directly related to the soil plant nutrient availability, soil water availability, right? As we have discussed till now. And in the last lecture, we have started about the sorption of pesticide, right, on the soil. So pesticide sorption in the soil is a crucial process that determines the fate and mobility and viability of the pesticide in the environment. So sorption is primarily refers to the interaction between pesticides and soil components. It influencing their transport, degradation, potential to contaminate groundwater. Sorption, either it is adsorption or absorption, both are included in that. And generally, when we are talking about the soil, we are primarily uh, taking care of adsorption. Okay, so whenever let's assume this through one example. Suppose this is the soil column. Okay, soil column means this is a cylindrical pipe. Let's assume this is cylindrical pipe. In that we have filled the soil. Okay, this is the soil. Now let's assume that This is the soil having filled with the same bulk density throughout this cylindrical pipe. So, and this is beaker, right, to collect. And okay, before that, let's assume we are putting water in this soil, above this soil, and this water contains the pesticide water. Okay, this water with pesticides or other chemicals, you can assume. So whenever we'll fill this with the this contaminated water, pesticide contaminated or fertilizer water, okay, what will happen? As you can see this, whenever we have water, so in that we have only water molecule. Okay, but as we are injecting fertilizer or pesticides also through this water, so it have this type of dissolved compound of pesticides and fertilizers, right? So whenever we'll add this water in this soil column, the soil have capacity to retain these particles, fertilizer and pesticide particles. Okay, so due to that, what will happen? The movement of water and this fertilizer and this pesticide or fertilizer particles is not same, right? So what will happen? The water will come after some time. Whatever if we are adding continuing continuous water on this top of this soil, what will happen? This water will come down eventually. Okay, but pesticide will not come as quickly as water. And why it is like that? Because this, this all these compounds will initially adsorb on soil particles. Okay, and this generally we are defining by partition coefficient. Before we will focus in detail on this concept, let's understand the importance of pesticide sorption in soil. So if particular soil have a higher sorption capacity, so it generally reduce the leaching of these contaminants into the groundwater. By binding to soil particles, pesticides are less likely to percolate into the groundwater. It influences the pesticide efficacy. So whenever particular soil have a higher sorption capacity, due to that, if it is not moving down, it means it is retained on the top surface, and it is available throughout the crop season, right? It means farmers require lesser pesticides or fertilizer. Then it's affect degradation and persistence. So sorption can slow down microbial degradation, right, as it absorbs on soil and leading to longer pesticide persistence in soil. It also prevents surface runoff, and if to happen surface runoff contamination, it required higher force, right? Then if we talk about the mechanism of pesticide sorption, so it is the adsorption by soil components. It is inner sphere complex formation and partitioning into organic matter. So adsorption on soil components is generally affected by clay minerals, organic matter, iron and aluminum oxides, right? While inner surface complex formation, so some pesticides form strong bonds with soil colloids through ligand exchange, making them less mobile, while some of uh, the pesticides also have a higher attachment towards organic matter. So due to that, all this mechanism affects the by pesticide sorption. Now, there are generally two terms that defines the sorption capacity of pesticide. So that is the partitioning and distribution. So the key difference between partition coefficient and distribution coefficient is partition coefficient refers to ionized and unionized chemical species, right? So partition coefficient, it measures the ratio of pesticide concentration on solid or soil to that in a solution, while distribution coefficient KD represent ratio of amount of pesticide sorbed by soil to the amount of remaining in the solution. It determines how much pesticide is available to movement in soil. Right. Then we have covered this important concept related to the role of clay mineral in the sorption. Right. As clay minerals or clay silicates have a higher cation exchange capacity, uh, it means interlayer space able have a higher and strong, and it retains the pesticide strongly, right? While one clays have a lower surface charge and smaller surface area result in a weaker pesticide absorption. Okay, so this is the summary of this last week, week number 5, right? So the key takeaways from this uh, week content is basically we have covered about 5 important things, right? So that is silicate clays. What is silicate clays? Its types, right? So silicate clay is basically type of colloids, right? And we are classifying them in the 4 major types that we have covered. Then silicate clay's properties and how it is affecting cation exchange capacity. So then we have started learning about cation exchange capacity. Then various type of sources or sources of charges for silicate clays. So that is either permanent charge or temporary charge, and how again it is related to the cation exchange capacity. Then we have lastly talk about the sorption of any chemicals onto the soil, and generally we have in this last topic we have talked about pesticides. So okay, uh, and also we have covered about relation of various soil properties in with the cation exchange capacity, right? So till now, if you have any query, anyone, you can ask. Hello. If you have any query, anyone, you can directly ask the chat box. Okay. You can also write, give an email ID. So, okay. Before we move on our next section, that is on MCQ type of questions. Let's take small break here of 5 minutes. Then we'll rejoin. Okay. Let's resume our session. I hope my slides are visible. Okay. let's resume our session. I hope my slides are visible to you. Okay, let's begin MCQ type of question. So we'll solve here a few important questions that is related to the week 5. Question number 1. Clay in water is an example of a dash type of colloid. So we know that clay in water is a type of, either it is a, which type of colloids according to you? It is solid in liquid, right? So it is A. Correct option is A, right? Because other option is not relevant, because liquid in gas colloid is colloidal system where liquid droplets are dispersed in a gas medium. Generally, like clouds, fogs, mist, aerosol, all this type of are types of liquid in gas colloid, while solid in solid colloid is whenever a colloidal system where solid particles are dispersed in another solid medium like colored glass, alloys and gemstone rubies. So clay in water is known as solid in liquid type of colloid. Correct answer is A. Question number 2. Single or double chains of tetrahedra are called. Single or double chains of tetrahedra. So before we discuss this type, before we solve this, so let's understand these types. So we know that nasosilicates is also known as island silicates and consist of isolated SiO4 tetrahedra and are not linked with each other but are instead held together by cations such as magnesium and iron. While sorosilicates, it also known as double tetrahedral silicates, and inosilicates having a commonly called chain silicates and can be divided into single chain and double chain silicates. So inosilicates is type of have a double and single and double chains of tetrahedra, generally that known as inosilicates, and phyllosilicates are known as sheet of silicates, right? So, and generally it consists of tetrahedral sheets where each SiO4 tetrahedral shares 3 oxygen atoms, and this type of phyllosilicates generally or commonly found in a clay type of soil, and it is very important for them to that contribute to the higher cation exchange capacity. So correct answer is option C. Question number 3. What is the criteria for isomorphous substitution? Right. So whenever we discuss about the source of charges on silicate clays, then that time we have discussed about isomorphous substitution. So we know that isomorphous substitution is the process where one ion replaces another similar size and charge within the crystal structure of the mineral without significantly altering the mineral structures. And this substitution occurs primarily in clay minerals and silicates, affecting their cation exchange capacity, surface charges, and nutrient retention. So, for example, whenever this silicon ion Si4 plus is replaced by magnesium, and at that time what will happen, there is a net charge of creation that is of -2, right? So and this type of substitution by similar size but of different charge ionic substitute or ionic composition is known as isomorphous substitution. So correct answer is element should have a similar size. Okay, right. These are not related to the isomorphous substitution. Correct answer is option A. Which of the following clays has a no swelling capacity? We know that kaolinite and let's first discuss these two important options given here, kaolinite and montmorillonite. So kaolinite and montmorillonite are two important types of clay minerals and differing in structure, properties and behavior in soil. So kaolinite is generally having a one gem, one type of clay mineral consists of one silica tetrahedral sheet and one alumina octahedral sheet per unit layer, right? It has a low shrink swell capacity due to strong hydrogen bonding between layers and making it stable, non-expansive and relatively low in cation exchange capacity. So what is the reason behind the low cation exchange capacity and stability of the kaolinite is strong hydrogen bond, right? As it have a strong hydrogen bonding between layers. If you see this example of kaolinite that contain one tetrahedral and one octahedral sheet, right here. So this is joined by strong hydrogen bonding and that, that directly related to the lower cation exchange capacity, lower shrink swell capacity and stability of kaolinite, while montmorillonite is a two gem one type of clay minerals, right? We know that because it have a two tetrahedral sheet and one octahedral sheet, and that allows for a significant shrink swell behavior as water and cations can enter between layers. So if you can see this, water and other cations will enter between this layer and that will generally related to the shrink and swell behavior of soil, and due to that it have higher cation exchange capacity, making it important for soil fertility and nutrient retention. Due to its expanding nature, montmorillonite is often found in dirty soils and used in applications like drilling muds and industrial sealants. Right. So, what is the answer? No swelling capacity having kaolinite, right? That have a no or minimum swelling capacity. Question number 5. Which of the following is an example of trioctahedral mineral? Various option is given. Glaucophyte, muscovite, A and B both, and none of the above. So we know that glaucophyte and muscovite are both mica group minerals and belonging to 2 gem 1 type of clay mineral where two mica tetrahedral sheets surrounded an alumina octahedral sheet, right? And glaucophyte is the magnesium rich mica and commonly found in ultramafic and metamorphic rocks. So here what they are asking, example of uh, trioctahedral mineral. So you know that full leucophyte is type example of trioctahedral mineral. Question number 6. The pyrophyllite is a 1 gem 1 trioctahedral mineral. No, this is not true as we have covered in this uh, uh, summary slides also. This Pyrophyllite is 2 gem, one type of dioctahedral clay mineral, right? It is consist of two silica tetrahedral sheet surrounding an alumina octahedral sheet. So it is correct answer. Means question number 7. The kaolinite is it is 1 gem, one type of clay, right? Because we know that kaolinite is 1 gem, one type of clay because it have one tetrahedral sheet and one octahedral sheet, and it have a very high hydrogen strong bonding between these two sheets that basically governs through its stability, and due to that it have a we cannot replace any uh, compound present on this mineral or clay type. Due to that it have a higher stability and lower cation exchange capacity, lower swelling and or no shrink swell behavior. And the correct answer is option D. Okay. Yeah. So all this related to the kaolinite. It is poor nutrient capacity, no shrink swell capacity, and 1 gem. It is 1 gem, one type of clay. And here the structure of kaolinite and distance between two kaolinite structure is 7 angstrom. Question number 8. Which of the following colloid has the highest cation exchange capacity? So option given is smectite, vermiculite, humus, and chloride. Right. So we note that humus has the highest cation exchange capacity among the given option due to its higher surface specific surface area, negative charge, and organic nature, allowing it to hold and exchange a large number of cation essential for plant. While smectite is 2 gem, one type of clay with high shrink swell capacity and moderate to high cation exchange capacity. Verticulite, vermiculite, sorry, is another 2 gem, one type of clay, but it have a higher cation exchange capacity than smectite due to more interlayer cation retention. Right. As you can see this in this figure also, and lastly is chloride. So chloride has is 2 gem, 1 gem, one clay type of mineral and has a low cation exchange capacity due to additional hydroxide interlayer. You can see this, right? Presence of hydroxide in chloride structure were smectite and vermiculite. If you see this, the distance is higher in case of smectite, that is 1 gem 2, while vermiculite have a low distance, that is about 1 to 1.5 nanometer. And smectite is, we know that this 2 gem, one type of silicate clay, right? Both smectite and vermiculite, and that leads to the its cation exchange capacity. So correct answer is humus that have a highest cation exchange capacity followed by vermiculite, then smectite and chloride. So correct answer is option C. Sorry, this is C. Okay, humus. Question number 9. Which of the following statement is true? In the inner sphere complex, ions are tightly binded with colloidal surface. the outer surface complex, ions are tightly bound with the colloidal surface. So let's understand this. Okay, so we know that in the inner sphere complex, ions form direct chemical bonds with colloidal surface without presence of water molecule in between, making attachment strong and stable. In contrast, outer sphere, right, where outer sphere complex involves ions that are loosely held on colloidal surface with layer of water molecules between them, and that leading to the weaker and more reversible attachment. Means this are replaceable, right? Whatever ions attached on outer surface are replaceable, and there is a weaker that is attached with a weaker force. Since only ions inner sphere complexes tightly binds the ions. So correct answer is option A. Inner sphere complex ions are tightly binded with colloidal surface. Now question number 10. The unbuffered method of estimating the cation exchange capacity measures. Unbuffered method estimating cation exchange measure the effective cation exchange capacity, right? So option correct is maximum. No, it is effective cation exchange capacity, which represent the sum of exchangeable bases and exchangeable acidity at the soil's natural pH. What is exchangeable bases? That is easily exchangeable like calcium, magnesium, potassium and sodium, while exchangeable acidity is aluminum and hydrogen ions. So correct answer is option A. When if we talk about maximum cation exchange capacity, contrast refers to the total exchange capacity of the soil when measured at buffered high pH, usually around 7 and 8.2, and difference between maximum cation exchange capacity and effective cation exchange capacity represent the additional cations that could exchange under higher pH conditions. Question number 11. The cation exchange capacity is expressed as the number of moles of positive charge adsorbed per unit mass. Right. So this is correct. So we know that based on the definition, it is true because it means cation exchange capacity measures the soil's ability to hold and exchange positively charged ions. And generally, by definition, we can say that moles of positive charge absorbed per unit mass, and typically we are measured in centimoles of charge per kilogram of soil or milliequivalents per 100 grams of soil is known as cation exchange capacity. And CEC is an important property influencing soil fertility and other nutrient holding capacity. Question number 12. Strength of adsorption of common cations on most colloids is follows orders of. We know that it starts from aluminum, calcium, magnesium, potassium, and ammonia equal, then sodium. So correct answer is option A. Question number 13. High potassium levels are known to limit the uptake of which element even when significant quantities of magnesium are present in soil. So high potassium levels in soil interferes with the uptake of magnesium, right? Due to cations competition on root action side. Let's read. Hi, Payal.
Hello, sir.
Let's resume our session. So, high potassium level affects the magnesium, right? Limit their uptake by plant. Because calcium can absorb, can also be affected by high potassium level, right? So after magnesium, there is a calcium that also affects if there is a high amount of potassium present in a soil. Correct answer is B. Question number 14. Which soil has a more leaching of pesticides? You know that pesticides is a chemical that we are generally using to kill harmful pests, right? Insects available on the soil. And if we talk about the leaching, so what is leaching? Leaching is generally movement of this uh, chemicals, any chemicals into the groundwater, right? So suppose this is our soil, agriculture soil. This is top soil layer, right? Agricultural soil, and we have grown various crops. And what we are doing in agricultural field, we are applying fertilizer or chemicals. Whenever we apply this type of chemicals, so this chemicals also moves along with the water, and this movement will generally depend on the type of soil. So whenever we have the clay type of soil, it means it have a higher specific surface area and it have a higher adsorption capacity. So due to the higher adsorption capacity, there is higher lesser leaching, right? Leaching means lesser leaching towards groundwater. While silty soil, we know that silty soil is in between the sandy and clay soil. So this is also clay content is relatively higher, but it is lesser than clay soil. So it means it also retain this type of pesticide and lower the leaching. While sandy soil, it mostly consists of sand type of particle, and due to the higher particle size and also the lesser water holding capacity due to the larger pores, what will happen? Particle will not hold or not absorb this pesticide. So ultimately, in sandy soil, you also observe that water movement is very fast. So along with this water movement and macropores, what will happen? There is a leaching, more leaching of pesticides as compared to the clay soil. So correct answer is option C. Question number 15. So base saturation, percent base saturation is given by calcium plus magnesium plus potassium divided by cation exchange capacity in 100. So it is correct, right? This know that this is the correct formula for calculation of base saturation. Now question number 16. Which of the following is correctly defined the soil colloids? We know that soil colloids is whenever soil particle size is smaller than 2 micrometer including clay and humus fraction, that is known as soil colloids. And the soil colloids is plays very important role in soil water holding capacity, cation exchange capacity, water holding capacity. So correct answer is all of the above, right? Because soil colloids also two-phase system where finely divided phase is dispersed in another phase. And this is a highly chemically active and crucial for ecosystem functions. Question number 17. Which of the following characteristics define the crystalline silicate clays? You know that four type of clays, right? Crystalline, non-crystalline, iron and aluminum based, uh, and finally humus. So crystalline silicate clays have a layer structure that consists of two or four sheets per layer and forming a different type of clay such as kaolinite, smectite, vermiculite, right? And it is a predominantly negative charge, primarily due to amorphous substitution, cation exchange capacity is the all of the right. Question number 18. Which of the following is characteristics of non-crystalline silicate clays? So we know that non-crystalline silicate clays do not have an ordered and crystalline structure like their crystalline counterparts. Instead, they occur in amorphous forms commonly found in volcanic soils such as immogroid, right? So generally, they have a higher water holding capacity and low stickiness. Their unique physical and chemical properties influence soil fertility, structure, and plant nutrient availability. So correct answer is here option B. They possesses both positive and negative charges. Which of the following statement is about humus is true? So humus we know that it is the part of soil colloid and humus is the smallest of all colloids and also have a highest cation exchange capacity, highest water holding capacity. Also, this net charge on the humus is always negative. So, which option is correct for this? It's not net charge is always negative. This is also incorrect. It has a very high water absorption capacity. So, option C is correct here, right? Question number 20. Which of the following factors is not used to distinguish crystalline silicate clays? So, number of and combination of structural unit. Crystalline silicate are classified in the as a tetrahedral and octahedral sheets. So option A is correct, but let's also see other important information. The type and bonding between layers and strength of bonding between layer silicates varies, and based on that, we can generally classify the silicates. Then number of cations in the octahedral sheet that also we are using to classification. So correct answer is here presence of organic humus content that we are generally not using to distinguish crystalline silicate clays. Right, all other options we are using. Here we not used correctly. Read the question, then answer. Right, in your NPTEL exam also, it's very important question. Question number 21. Which of the following statement is true about 1 gem 1 silicate clay? So it consists of one tetrahedral and one octahedral sheet per layer. We know that. And 1 gem 1 silicate clays are characterized by their layered structure where each layer consists of one tetrahedral and one octahedral sheet. It has a high swelling and shrinking capacity. This statement is incorrect because we know that 1 gem 1 structure like kaolinite that have no shrink swell capacity, while it is synthesized under unequal concentration of aluminum and silicon. This is also incorrect, right? Because 1 gem 1 silicate clays are typically formed when aluminum and silicon are present in an equal concentration, right? That leading to balanced structure within with limited cation exchange capacity. While on the other hand, Montmorillonite is a common type of 1 gem 1 clay structure. No, it is also wrong because you know it is a 2 gem 1 type of silicate clay group, whereas kaolinite is a 1 gem 1 type of group, and it is known for its lower specific surface area, lower cation exchange capacity, and strong interclay bonding. So correct answer is for 1 gem 1 silicate clays, it consists of one tetrahedral and one octahedral hedral sheet per layer. Question number 22. Which of the following factors primarily affect the adsorption of cations and anions in soil? Soil pH and surface charges of colloids, soil moisture content, presence of sand particles, and organic matter oxidation. We know that soil pH and surface charges on colloids is the mainly that affects the cation and anions adsorption on the soil colloids, and we know that that is known as permanent charge and temporary charge, while other option are incorrect because like soil moisture that affects the ion mobility and nutrient availability, but it does not directly control the adsorption of the cations and anions. Adsorption is mainly an electrostatic interaction between charged soil surface and ions. Also, presence of sand particles. So we know that sandy soils have a lower cation exchange capacity due to their coarse texture, means higher specific surface area, and due to that it have minimal clay and organic matter, so it is not directly affecting adsorption. While organic matter oxidation, so it is also incorrect because organic matter, we know that it plays important role in nutrient retention, but its oxidation leads to mineralization, releasing the nutrients rather than absorbing them. Right? So whenever there is oxidation of organic matter, that leads to the mineralization and that ultimately release the nutrients instead of absorbing. So correct answer is option A. Option A. Okay. Question number 23. Which of the following statement is true about kaolinite? You know that it is a 1 gem 1 type of structure and have a lower cation exchange capacity. I am not doing in detail because we know this and we have already discussed this in detail throughout this uh, throughout this lecture. Which of the following statement is true about smectite? So smectite is 1 gem 1 type of clay mineral? No. It have a high shrink swell capacity. Yeah, that may be right. Let's see other option. Low cation exchange? No. It is a non-expanding due to strong interlayer. So correct option is option B. We know that smectite is 2 gem 1 type of clay mineral group, meaning it consists of two tetrahedral and one octahedral sheets, and it has a high shrink swell capacity due to weak van der Waals forces in interlayer spaces. Okay, which allow water molecules to enter and exist, and that generally develops condition like this, right? So question number 25. Which of the following statement is true about Montmorillonite? So Montmorillonite, we know it has a high shrink swell potential because Montmorillonite is a member of smectite group. As you can see here, the Montmorillonite mineral figure, and it have a high shrink swell capacity due to weakly held interlayer cation and water molecules, and also weak van der Waals force between two layer. This property makes it expansive and leading to problem in engineering applications such as road construction and building formation. So Montmolionite type of clay structure is not suitable for construction, and it is belong to we know that 2 gem 1 type of clay mineral is the common, and this type of structure have high shrink soil capacity, and that is of about 80 to 150 centimole per kg. So correct answer is option A. Which of the following factors primarily contribute to variable charge on colloid? So that we know that that is pH, and pH is generally protonation and deprotonation of surface hydroxyl group, right? So this is the correct answer. And generally we know that pH is uh, uh, protonation and deprotonation of surface hydroxyl group because of variable charges on salt surface colloids primarily arise due to this pH dependent reactions. And like hydroxyl group present in a clay minerals, organic matter and oxide surface, and at a lower pH, colloids gains protons becoming positively charged, while high pH they lose protons acquiring negative charge. Other options we know that isomorphous substitution, that is permanent due to the permanent charge, when same size but different charge replace the constituents, and other we are not going in detail. So correct answer is option B. Which of the following factor has the most significant influence on cation exchange capacity on soil? So cation exchange capacity, which of the following? The soil texture and clay mineral type. Okay, bulk density, no. Soil compaction, no. pH dependent, permanent charges only. So this is little bit tricky question. Let's see its explanation. So soil texture and clay mineral type. This is the most significant option because cation exchange capacity mainly depend on the soil texture, like the presence of clay minerals. Because if there is a high presence of clay minerals, it means a higher specific surface area. Higher specific surface area means, and also if there is a high presence of smaller particles like K, it have a negatively charged ion, and that negatively charged ion attracts more cations. So it have a higher cation exchange capacity. So correct answer is option A. While bulk density, we know that it is not related because it is generally defined mass per unit volume, and it affects soil porosity and root penetration. Similarly, soil compaction also is not related here. And if we talk about pH dependent, independent permanent charge only, this is also incorrect because some clays like smectite and vermiculite have a permanent negative charges. And cation exchange capacity also influenced by pH dependent charges from organic matter and oxides. Okay, question number 28. Which of the following cations is the most commonly found in the exchangeable cations pool of agricultural soil? We know that calcium, that is the correct answer, because calcium is the one of the dominant exchangeable cations in the most agricultural soil. It is primarily derived from weathering of minerals like feldspar and calcite, and strongly retained on soils colloids due to its divalent charge. So correct answer is calcium, right? So to summarize, okay, I think this is the last question. Okay, we have one more question. Question number 29. Percent base saturation is calculated using which of the following formula? So we know that correct answer is option A, that is exchangeable base cations divided by cation exchange capacity. Why? Because base saturation percentage represent the proportion of cation exchange capacity occupied by essential cations like calcium, magnesium, potassium, and sodium. A higher base saturation generally indicates better soil fertility since more nutrient cations are available for plant uptake. While exchangeable anions to cation exchange capacity, this is incorrect because this is here defined as anions. So base saturation is generally defined as exchangeable base cations, not anions. So exchangeable base cations divided by cation exchange capacity into 100. So correct answer is option C. So this is the end of today's session. Okay. So the to summarize this session, and I can say that the key takeaway from this lecture is we have discussed about the importance of silicate clays, different type of silicate clay structures, how their formation affects the cation exchange capacity due to the various forces like van der Waals forces and strong hydrogen bond between that layers, particularly tetrahydrate and octahydrate silicate structures. All this will directly affecting cation exchange capacity, and cation exchange capacity also after that we have covered important topic related to the soil sorption of pesticides on the soil, or generally we can say the sorption of any chemicals on the soil, and that is very important to understand because what we're applying large amount of chemicals on our agricultural soil, and these chemicals have a prone to contaminate our groundwater resources in various soil types. So once we have understanding of this type of silicate clays mineral present in our soil and its cation exchange capacity, or either one of the important properties like distribution coefficient or partition coefficient of soil, we can generally decide the various management practices like how much how much or at what time we need to apply the our fertilizer or chemicals in agricultural soil, right? So with this we are ending this session, today's session. So again, thank you so much. So before we close, I request you to watch this previous content and today's session if you missed this in live during live session. Also, I'm uploading all this lecture material in this Google Drive, so you can directly click on this link and uh, found this. Also, I'm requesting you to provide your valuable feedback through this Google link, Google form, where you can provide your view on the session. Like if you if you want to cover some specific topic or some specific manner which is not covered during the session, you can write through this Google form. Also, if you have any query, you can also write to the provided email ID or course forum. Okay, I'm ending this session here. So thank you so much for joining. Thank you.